So in this problem we have again a charged rod, and it is placed on the x-axis extending from x is equal to minus a to plus a, and it has the total charge q, so the charge density is just q divided by 2a. This time the question is, what is the potential of any point which lies on the y-axis, and it has a distance b to the center or the origin of the coordinate system. And what we do again, of course, we divide this charged rod into small pieces which we call dq, because each piece has a charge dq, and express the potential of these dq's on this point. And let's choose a dq which is away from the origin at a distance x, and the distance of dq to the point in interest is called r, and dq may be expressed again in terms of the line charge density times dx, and this forms a right triangle x, b, and r, and so that means we can express r in terms of b and x by the geometry. R is the hypotenuse of this right triangle, and it is in square root b squared plus x squared. So we express the infinitesimal potential created by the infinitesimal charge dq at this point as k times dq divided by r, and if we write down all the terms explicitly in terms of the variable x, we get k lambda dx divided by x squared plus b squared in square root. Next, we should integrate to find the total potential from x is equal to minus a to plus a, and the integration of this quantity can be found from the integration tables, or it can be integrated by using the change of variables. So simply it is the logarithm x plus in square root x plus b squared, x squared plus b squared, and we evaluated at the endpoints of the integration. So the final result is the potential at any point which lies on the y-axis, a distance b away from the center of the rod, is expressed as k times lambda times the natural logarithm a plus in squared a squared plus b squared, and divided by minus a plus in squared a squared plus b squared. So again, we have the question of if we release an electron on the y-axis from y is equal to square root 15a, the question is, what is the speed of this electron at y is equal to square root 3a. So again, the change in the potential energy of the electron will be equal to the kinetic energy gained by the electron, because it is released from rest. So the final speed may be expressed in terms of the potential energy, and the potential energy is just the charge q in general times the potential difference, and we have already obtained the potential of any point on the y-axis. So instead of q we will replace minus e, and if we put the final points, also the difference of the potential at the final points, we express this change in the potential energy as the electron charge times the Coulomb constant k times lambda the charge density times the natural logarithm 5 divided by 9, and this will be equal to the speed in terms of, as we put everything in this energy equation, in square root 2k lambda e divided by the mass of the electron times the natural logarithm 5 divided by 9.